Okay, in the previous integral, or the previous video, we had considered the integral of the hyperbolic secant of x dx, and we expressed this integral in terms of the basic definition of the hyperbolic secant of x dx, and we kind of went along that path there, and eventually we did grind out an answer to the integral. It was kind of a grueling experience, and we got a long, complicated answer. And we explained that, yes, to us, we don't see anything wrong with the approach. We don't see anything wrong with the answer. But if you look it up in a table of integrals for what the answer is to this, it is not what we derived in the previous video. So there's another approach that we can use here, and that is, if you remember now your hyperbolic identities, the hyperbolic secant squared of x plus the hyperbolic tangent squared of x equals 1. So a hyperbolic secant of x, that would equal the square root of 1 minus the hyperbolic tangent squared of x. And notice that if we rewrote the integral like that, let's just do it right here, we have the integral of the square root 1 minus the hyperbolic tangent squared of x dx. Notice what you have here. Constant minus a variable squared. And before I proceed further, let's write this a little bit bigger. Okay, this integral here is equal to the integral of the square root of 1 minus the hyperbolic tangent squared of x dx. And once you have it in this form, this just screams out to solve with the trig substitution. We have a constant minus a variable squared, and the trig identity, hopefully that reminds you of, is the cosine squared theta equals 1 minus the sine squared theta. Here we have a constant minus a variable squared. Here we have a constant minus a variable squared. They're the same general format. So we make the substitution and say, let the hyperbolic tangent of x equal the sine of theta. Now if we do that, this would be 1 minus the sine squared of theta, which is the cosine squared of theta, and we're taking the square root of that. So this right here becomes the cosine of theta. Now what about the dx part? Well, let's take differentials here. This is this hyperbolic secant squared of x, and that would have to be equal to the cosine of theta d theta. And we forgot our dx here. Let's rewrite this. This would be the hyperbolic secant squared of x dx. And the derivative of the sine of theta is plus the cosine of theta d theta. Now, what about this? Let's go up to here. The hyperbolic secant squared of theta equals 1 minus the hyperbolic tangent squared of theta. Let's write that in here. 1 minus the hyperbolic tangent squared of x dx equals the cosine of theta d theta. But we have our substitution here. So this is going to be 1 minus sine squared of theta, which is the cosine squared of theta. So we have here the cosine squared of theta with our substitution times dx equals the cosine of theta d theta. And since we're making a substitution now in terms of theta, we want to have dx expressed in terms of theta. So dx, divide both sides by this, equals d theta divided by the cosine of theta. So let's go back to our integral here. We have this. This is the cosine of theta. This is the cosine of theta. Dx, that is d theta divided by the cosine of theta. So this is just theta, the integral of d theta, which is theta. And now we go back up to our substitution here. Theta is going to equal the inverse sine of the hyperbolic tangent of x. So we go back now to our original integral. The integral of the hyperbolic secant of x dx equals the inverse sine of the hyperbolic tangent of x plus an arbitrary constant. And that indeed is the answer. If you look up in the table of integrals, this is what you're most likely to see. And it's not difficult at all getting there, much shorter than the previous video. But we want to make a point, and that is, if you're solving a problem and you're not getting anywhere, or it seems to be an awful long way to get to the solution, think of all the approaches that you have. If one approach doesn't work out, very likely another approach might be a better way for you. Okay, anyway, that's it for this video. Come back and join us for some more videos, and we'll try and tackle some more hyperbolic integrals.